Question 9 and 10 is based on a game. In a game played by two people, there were initially n matchsticks kept on the table. Okay. A move in the game consists of a player removing either one or two matchsticks from the table. The one who takes the last matchstick loses. Okay. So I will take either one or two matchsticks out of any number of matchsticks kept on the table, and my opponent will also then get his or her turn to take one or two matchsticks. Players make moves alternately. The player who will make the first move is A, so whoever makes the first move is called A. The other player is B, so B will make the second move always. Okay. Before we figure out how to play this game, obviously we understand what it is to win and lose. Let's quickly take a look at both the questions to align our thinking. What should we think about? Because at this point we might have to do double duty work by having to think about how A will play the game and about how B will play the game. Basically, in any game, it will be equal to the number of players. You'll have to think from everybody's perspective. Let's see if that's required. The smallest value of n that ensures a win for B is, and the largest value of n that ensures a win for B is. So both questions require me to understand the game itself, the context itself from B's point of view. So what does B have really as a guarantee? And let's think only about B. B always plays second. So no matter what A does, B can react to it because B will start the game second as well. Now what can B do? Let's see. A can take one or two matchsticks. B can take one or two matchsticks. If we were to operate only in this and try and find out what is B's control. Control is a point that B can always make constant. In any game, any player going second is trying to first neutralize what the other person does or use that same neutralization to actually win. If I can stop you and win at the same time, that's the best option. Now what do I have the most control over? If A picks one or two, B can pick one or two. So a total after each round of two can be either 2, 3 in two cases and 4 in one case. So it's in one case it can be 2, in one case it can be 4, in two cases it is 3. This is when B picks 1, A picks 2, when B picks 2, A picks 1. The 3 is constant. No matter what A does, B can pick the number of matchsticks required to make it a multiple, to make it exactly 3. So every deduction is going to be that of 3. And I have been told 1 needs to be left over for A. That means after B's turn at some point in time, there needs to be 1 left over. So literally any number, if I keep dividing it, which finally gives a remainder of 1, if I keep subtracting 3 from it, will be a solution by which B can always win. Because no matter what A does, B will simply reduce it to a factor of 3. If there are, let's say, 4 matchsticks, A will take 2, B will take 1, A will take 1, B will take 2. A will always have 1 remaining. Same thing with 7. Any multiple of 3 plus 1 basically. Now let's look at the options given. Yeah. In the question 9, the smallest value of n greater than 5 is of course 7. That ensures a value of win for B. And in 10, largest value of n lesser than 50. Well, that's any multiple of 3 plus 1. So 48 is the largest multiple of 3 here, plus 1, 49. That's option D. That's how B can always win. The key here was to realize this was a question of quotient remainder and divisibility as a function rather than looking at a game as some random things that have been asked to do. You can reduce every game to a sequence of mathematical moves. Even chess can be played by a computer. And I'm sure you would have heard of the example where this IBM's Deep Blue, one of the most advanced supercomputers to play chess, beat, I think in one games out of three or two games out of three, Garry Kasparov, world grandmaster in chess and best in the world at that point in time. The wondrous thing here is not the fact that the supercomputer beat the human two times out of three or one times out of three. At least one time out of three, the human being won. And it wasn't doing the billions of computations that the supercomputer was doing in processing, in finding out all ways of looking at everything, trying to figure out what is millions of moves, calculating each one of them. Garry Kasparov couldn't have been doing millions of moves in his head. He knew which ones were important, which ones were prioritized. Those thoughts, those moves would come first in his head, not the unnecessary ones, which a computer can't possibly replicate. And so, when you are thinking through these questions, you need to think like a human being with elegance and try and figure out what is the fundamental threads that are connecting these questions that make the whole thing sensible and rational, subject to constraints, subject to equality signs, and any other information given in the question. And that's really it.